Hello everyone, welcome back to another tutorial. Today we're going to talk about a topic that's a very interesting topic, in my personal opinion at least, and it's the use of the conjugate beam method to find deflections and rotations or slope in beams. So what do you want to get out of this tutorial? Well, we need to know what CBM is, and we want to know why we use it. Then we're going to understand how and why it works. Then we're going to talk about the supports on the conjugate beam, the strengths and weaknesses of this method, and we'll finish up with some examples. What is CBM? Well, here's a definition I pulled out of the couple of websites I put together. Okay, so it says the conjugate beam method, CBM, is an engineering method to derive the slope and displacement of a beam where the conjugate or imaginary beam has the same length of the real beam, but loaded with the curvature diagram of the real beam and with supports that may differ from the original supports. Okay, let's take a look. To understand it, let us look at how would you calculate the displacement on a beam. How would you do it? Well, there are a couple of methods actually, but one method I went over in a previous tutorial was the double integration method. It turns out it's a little bit hard for some folks, but it's not as well precise and easy compared to this method. We will see the weaknesses and the strength of the CBM method, but let's just say that it's not an easy method, talking about the double integration, of course, in this case. Plus, the double integration requires the equation of the elastic curve of the beam. You need to derive the equation of the elastic beam. Well, what about CBM? We will see that it depends on statics, basically. So if you're good with statics, you should do good in using the CBM method, and it allows to calculate the slope and deflection without deriving the elastic curve equation of the beam. So that's a plus for the CBM method. You don't need to derive the equation. Okay, we may see a case or two where you need to derive something, but you don't need to derive the equation of the elastic curve of the whole beam. It allows you to find the slope and deflection at a specific point along the beam. So you don't need to find an equation that describes the displacement or deflection of the entire beam. You can, using this method, basically what you're saying that at this point, I need to know the displacement or the rotation. Okay, you don't need to know any other information regarding any other points along the beam. Before we jump into the CBM method, let's take a look actually at the relation among the load, shear, and the moment. I've done this in previous tutorials, but let's go over them very quickly. Let's take a look first at the shear force. The shear force can be defined as the integral of the load function. So basically what I'm saying here that if you have the load as a function, if you integrate it along the length of where this load is acting, basically you will get the shear force in a beam. For the bending moment can be defined as the integral of the shear force function. So basically you are integrating the load function twice. If you have the load function integrated twice, you'll get the moment. Okay, so basically this step here, mx double integration wx d square x, shows you that you need to integrate the load function twice to get the moment. If you define Wx mathematically, you can evaluate the above integrals to get the shear force and the bending moments for the beam. That said, now let's take a look at the relationship between the slope and the deflection. The slope of the beam can be defined as theta x, for example, is an integration m over ei dx. Alright, so what is m? M is the bending moment, E is the modulus of elasticity, and I is the moment of inertia of the beam. If we take a look at the deflection of a beam, it can be defined by double integrating m over ei. What do we call this m over ei? M over ei is referred to as the curvature of the beam. Do you guys see any similarities between having a single integration and a double integration in the case of the relations between the slope and deflection and the relation between the shear or the load, shear, and the moment? Let's take a look. We see that with single integration, if we integrate the load one time, we get the shear. And if we integrate the curvature one time, we get the slope. Now, if I double integrate the load, I'll get the moment. And if I double integrate the curvature, I will get the deflection. If we integrate the applied load once, we get the shear. And if I integrate the applied curvature once, I get the slope. And if I integrate the applied load twice, I get the bending moment. And if I integrate the applied curvature twice, I get the deflection. Still not clear? Let's dig deeper. Taking a look at this simply supported beam with a concentrated load P and the midspan. For this beam, the applied load is the load P acting on the beam. Extremely obvious. The moment diagram of the beam can be easily obtained, right? So this is the moment diagram. Now, if I divide the moment diagram by EI, I will simply get the curvature diagram. Now I need to treat this curvature diagram, which in our case looks like a triangular load, and apply it to the conjugate beam. Okay, I said conjugate beam. But before I dig into or jump into what is a conjugate beam, let's put some rules here. The direction of the applied load. I want to know the direction of the curvature diagram that I'm going to apply as a load on my conjugate beam, which I will talk about later, but let's set some rules, okay? If the sign of the curvature diagram is positive, meaning it's above the horizontal axis, the load should point in the positive y direction, or in other words, upward. And if it's negative, which means that the curvature diagram is below the horizontal axis, then the direction should be in the negative. Let's take a look at our case here. We have this curvature diagram, M over EI. Clearly, it's above the x-axis. So if I want to apply it to a beam, my conjugate beam is going to point upward this way. The question now, are we applying the load on the same original beam? No. Now we can talk about the conjugate beam. So what is a conjugate beam? For this method to work, the supports on both the real and the imaginary, or conjugate beam in this case, should satisfy some conditions. Let's take a look. We have a real beam and a conjugate beam. In the real beam, we know that if I integrate the load, I should get the shear. In the conjugate beam, if I integrate the curvature once, I get the slope. In the real beam, if I integrate or double integrate the load, I get the moment. And in the conjugate beam, if I double integrate the curvature, that is, I will get the deflection. For zero shear on real beam, I should have zero slope on a conjugate beam. And for non-zero shear on the real beam, I should have non-zero slope on the conjugate beam. Again, zero shear on real should represent zero slope on the conjugate, and non-zero on real should represent non-zero on conjugate. And the same thing applies for the moment. If I have zero moment on the real beam, I should have zero deflection on the conjugate. And if I have non-zero moment on the real beam, I should have non-zero deflection on the conjugate beam. But the question is how? Let's construct a conjugate beam. Let's do an example. Let us consider the cantilever beam. Here's a cantilever beam, AB, with a fixed end at A, and that's the real beam. Now, what do I mean zero moment here and zero deflection here, or zero shear here and zero slope here, and the things that I mentioned in the previous slide? So let's take a look at point A, for example. On the real beam, I'm still talking about the real beam. At point A, we have non-zero shear and non-zero moment. Of course, it's a fixed end, so I should expect a reaction. It's either going up or down depending on the direction of the load applied on this beam. And because it's a fixed end, it should resist bending, right? So there is a non-zero moment. So the conjugate beam, the point A on the real beam, can be seen as point A prime on the conjugate beam. Now, if I have non-zero shear and non-zero moment at A, I should have, and that's what I need, non-zero slope and non-zero displacement. Now take a second and let this sink for a while. What kind of a support or end condition that will provide you with non-zero slope and non-zero displacement? If you really think about it, you need a free end, right? Because at any free end, there is non-zero slope and non-zero displacement, because the free end is free to rotate and displace. It can rotate counterclockwise or clockwise, and it can move up and down. So what you need to do is make the point A prime a free end. Now let's take a look at point B. Now at point B we have 0 shear and 0 moment, because point B is basically a free end. So what do I need at B prime? At B prime, I need something that a support condition or an end condition that will have 0 slope and 0 displacement. And what kind of end condition that have 0 slope and 0 displacement? It's basically a fixed end. The conjugate beam and the real beam, you can take a look at them on the screen right now. The fixed end became a free end, and the free end on the real beam became a fixed end on the conjugate beam. Now this is the conjugate beam that I will apply the curvature diagram I created or I ended up with. Then I will try to finish the problem from here. Let's recap. What do we know so far? We know how to change the real beam to a conjugate beam, at least one example. I'm gonna go over a couple of them. We know how to get the curvature diagram, basically get the moment diagram of the beam divided by EI, and the new diagram is basically the curvature diagram, and apply it, take this curvature diagram and apply it on the conjugate beam. Basically what I'm saying, these are the steps you need to follow to solve the problem involving any conjugate beam. So before I go on, as I said here, let us look at other support cases. Let's assume that the one on the right is the diagram or the end condition on the right represents the real beam, and on the left is the conjugate beam, or vice versa, because you can talk about this back and forth. For this on the right, I have an exterior pin, whereas where I have a 0 moment, but I have some value for the shear. I need a condition on the conjugate beam where the deflection is 0 and theta, or the rotation, has a value. It turns out that the exterior pin on the real is the same as it should be an exterior pin on the conjugate, and same thing goes for the roller support. The fixed end on the conjugate on the left will have a 0 deflection and 0 rotation, so on the real it should have a free end, and that was basically the example we did. And of course, if you switch them, it's going to be the same thing. A fixed end becomes a free end, and a free end becomes a fixed end. Now what about this one? If I have a middle hinge where the moment is 0 and I have a value for the shear, I should have on the conjugate beam an interior pin where the displacement is 0 and the rotation is allowable. And same thing, a hinge, I can have a roller. And now, what if I have an interior roller on the real one? I should have a hinge on the conjugate beam. So let's go ahead and see our first example. So this is my first example. I have this cantilever beam with a constant EI. So E multiplied by I is a constant, meaning that the beam is made from a single material, and the moment of inertia is constant, meaning that the cross-section of the beam doesn't change along the length of the beam. And I'm asked to find the displacement at point B, where the point load P is acting. Now, what is the solution? Let's follow the steps I mentioned before. Change the real beam into a conjugate beam. We've done this when we discussed how to change our first real beam into a conjugate beam. Now, what's next? We need to get the curvature diagram, right? This is the beam, and this is the moment diagram, and if I divide the moment diagram by EI, I will get the curvature diagram. Third, apply the curvature diagram to the conjugate beam. This is the curvature diagram. Remember, the curvature diagram was negative, or in the negative region when I did it. So the direction of the curvature as a load, it will point downward. What does the conjugate beam method say? It says that the shear force at B prime should be the slope at point B if I'm talking about the real beam. So again, the shear force at B prime on the conjugate beam represent the slope at point B on the real beam. And the moment at point B prime in the conjugate beam will basically be the displacement at point B on the real beam. Meaning I need to solve for the shear force and the moment, right? So let's solve for the shear force first. So we take the summation of the forces in the Y. Basically, I will have 1/2 multiplied by L multiplied by PL over EI, which is the area of the triangle. I will concentrate it, and that's of course minus VB prime, set that equal to 0, and when I solve for VB prime I will get negative PL squared over 2EI, and that's the rotation on the original beam or the real beam at point P. Now what we really are looking for is the moment. So I need to take the summation of the moments about point B prime, but I need to concentrate the triangular load. If I do that, I will get 1/2 PL over EI multiplied by L, and that's the concentrated force, and it's acting at a distance 2L over 3, which is basically the geometrical centroid of the triangle. Now I take the moments about point B prime. If I sum the moments, I will have MB prime plus the force PL squared over 2EI multiplied by the distance, which is 2L over 3. I get negative PL cubed over 3EI. This moment MB prime is basically the displacement on the original beam at point B. And to double check, I pulled something from one reference I have. This reference lists all or most of the cases for simply supported beams or cantilever beams, and we can see right here that delta max at free end is PL cubed over 3EI, and our negative sign here says that the beam will move downward. Now let's jump into the second example. I have a simply supported beam with a point load P acting at point C, which is a distance B from the right and distance A from the left, and again I have EI as a constant, and I'm asked to find the displacement at point C, meaning the displacement under the point load. Again, follow the instructions, follow these steps, change the real beam into a conjugate beam. Take a look at this beam. The conjugate beam in this case will look exactly like the real beam, because in the real beam I need 0 moment at A and I need a shear value at A. That if I want to represent it using the conjugate beam at A, I would need 0 displacement, which is true at the left side of the conjugate beam because it's a pin, it cannot displace, and I can allow some rotation. Same logic you can follow for point B. Or if you don't want to bother, you just go ahead to the slide where I listed the cases, and you can say, oh, this is an exterior pin, so it stays an exterior pin, and this is an exterior roller, it can stay an exterior roller. Now let's get the curvature diagram. The curvature diagram of this beam, to get it, you need to find first the reactions. So the reactions, you can solve for this reaction, no time. PA over AB for the B support and PB over AB for the A support. Draw the moment diagram, then divide it by EI, which I did right here, and that's what you guys see right now is the curvature diagram. Take this diagram and apply it to the conjugate beam. If you do so, you will have this situation right now. Now, you need to find the reactions, because remember, you're trying to solve for the shear force at C and the bending moment at C. Shear force represents the slope, and because it's a conjugate beam, so if you find the shear at point C, you're finding the rotation, and if you find the moment at point C, you will find the displacement. So let's solve for the reactions. To solve for the reactions, I divided this triangular load into two triangles, and I concentrated the loads concentrated the loads from these two triangles like that. So the right triangle will have a load B over 2 multiplied by PAB over A plus B EI, and if I do the left triangle, it's going to be A over 2 multiplied by PAB A plus B over EI. Now, to find the internal shear force, the bending moment at C, we need to find one reaction. We don't bother solving for both reactions, okay? I will do it using the reaction at point B. I'll take the summation of the forces about point A, and if I do this correctly, I should end up having the reaction at point B. So By multiplied, that should be a B prime Y, but you get it. By multiplied by A plus B plus PAB squared over 2EI multiplied by A plus B, multiplied by the distance A plus B over 3, and again plus this quantity PBA squared over 2EI A plus B multiplied by the distance 2A over 3. And if I solve for BY, I'll get this quantity. Now I have BY. Why do I need BY? Because I'm going to take a cut at C and look at the cross section. So this is my beam, and if I want to find VC prime and MC prime, I will take this cut. And if I do so, I need basically to use my summation of moments and summation of forces to find the unknown MC prime and VC prime. And remember, I needed B, the reaction at B, so I will be able to use the summation of the forces and the summation of moments. So let's do the shear force first. So summation of F equals to 0. If I do the summation, I will get VC prime equals PAB over 3EI multiplied by A minus B over A plus B. And that is the rotation at point C on the real beam. Again, the shear force on the conjugate is the rotation or the slope on the real beam. Now let's do the summation of the moments about point C, or C prime in this case. And basically you can pause and figure out where I got these, but basically I'm taking the summation. It's a force times distance, all right? And if I solve for MC prime, I will get this quantity, which is minus P A squared B squared over 3EI multiplied by A plus B. So in summary, these are the things I have. The shear, which turns out to be, or I know the shear on the conjugate, which is the rotation on the real, and the moment of the conjugate, which is the displacement on the real beam. And to double check my answers again, I pull this from the same reference, and you can see here that delta A at point of load is P A squared B squared over 3EIL. A plus B is L, all right? And again, the negative sign is just telling us that this point on the beam moves downwards. Other issues. Again, what's the strength of this method? Well, depends on statics. We didn't do any funky business, right? Summation of forces, summation of moments, reactions, that's it. And it finds the slope and deflection at a point of interest without deriving the entire equation of the beam. Now, this is not that efficient in this case, all right? The CBM is efficient if the load applied was a concentrated load. And here's why. The concentrated loads produce a moment diagram of the first degree, straight lines I mean. And of course, if you divide them by EI, meaning the moment diagram, if you divide them by EI, the curvature diagram are still of the first degree. And if you take this curvature diagram and apply it on the conjugate beam and try to take a cut and find the resultant forces produced by a segment of a load, it's easier to calculate the area under the graph to concentrate the load, just like I did with the triangular loads. But let's see a simple case where it's a little bit inconvenient. We can get to the solution using the method, but it's not as straightforward as it used to be. Let's take the simplest case possible. A simply supported beam with a uniformly distributed load Wx and EI is constant again, and we want to find the displacement at midspan. So what is the solution? Find the reactions first. The reactions, you can find the reactions easily. W multiplied by L and divided by 2 because these two supports share equal amount of reaction. And the conjugate beam is same as the original. We've done this beam in the previous example. The curvature diagram, remember the moment diagram is WL squared over 8. That's the maximum value. Okay, so you have this diagram and you divide it by EI, you will get basically the curvature diagram. And since the moment diagram is above the horizontal axis, the curvature diagram should be applied on the conjugate beam, but pointing upwards. If I want to take a cut at midspan, trying to find the shear force and the moment, and the shear force again represents the slope and the moment represent the displacement at midspan in this case, you can see it's not that easy to find the resultant force caused by the parabolic shape. What to do? Well, here's what to do. Go back and find the equation of the moment diagram. You need an equation describing this curve, this curvature, okay? And again, take this equation, divide it by EI, and you'll get the equation for the curvature diagram. Now we have an equation. Come back and integrate. Use integration because, again, integration is nothing but finding the load under the curve, right? Or finding the area under the curve. And the area here represents the summation of the load or the concentration of this parabolic load. Then you basically continue the problem. So your only obstacle here is to find a concentrated force that can be represented by this segment. If you know how to do it using integration, you're done. What is the bending moment equation? Well, this is the bending moment equation. You can refer to one of the tutorials I've done before. How can you, it will show you basically how can you find the moment equation of this kind. And the curvature diagram is basically taking the moment equation and dividing it by EI, so you'll get this. So that's what we have right here. Now find the reactions. We need the reactions because remember we're gonna take a cut in the middle and we need to use statics, so we need the reactions here. So the reactions, take the summation of the forces in the y, and if you do that, it's a prime y plus b prime y plus, now this integral from 0 to L is basically the area under this curve or the concentrated force pointing upward resulted from the parabolic shape. And if you do that, you will basically, if you do the integration, you'll get WL cubed over 12. And if you take the summation of the moments about point B in this case, for example, and if you do that, minus a prime y multiplied by L minus the load times the distance, then you will get a prime y equals minus WL cubed over 24 EI, and of course b prime y is the same because the load is symmetrical. What if I take a cut at point C prime, which is at midspan, and I need to find V prime, VC prime, and MC prime? What I need to do, I should know that the moment is basically the integral of Fx multiplied by Wx over a distance between 0 and L over 2, which is the segment I'm interested in. One will ask, what is Fx? Fx basically is a distance function. Okay, a distance function can be represented by L over 2 minus x. So let's take a look at this distance function. If x was a 0, and I'm measuring x from the midspan toward the left, if x was a 0, the distance fx should equal L over 2, right? Now, if it's 0 at the midspan and it moves to the left, distance L over 2. So at A prime, x equals L over 2. If x equals L over 2, the function fx equals 0. If the function is 0 and you go back to the integration and you put a 0 there, the moment should be 0. And that's true because at A prime we have a pin support. We shouldn't have any moment. The W, or the load, basically is what we had before. All I need to do is perform this integration. So the moment caused by the distributed curvature can be represented as, just do the integration. And if you do the integration, you will end up having WL to the 4th power over 128 EI. Basically, that's the moment produced by the parabolic shape. Let's do the actual calculation of the moment. So the moment at C, I do the summation of the moments about C prime. This is the summation, MC prime plus WL square, WL to the 4th over 128 EI, which what we got from the previous slide, minus now WL cubed over 24 EI, that's the reaction, multiplied by L over 2. So I'm summing MC prime plus the M caused by the parabolic shape and the moment caused by the reaction at point A prime, and set that equals to 0. If I do so, I will get MC prime equals minus 5WL to the fourth over 384 EI. Now, this is the moment on the conjugate beam at point C prime. That means this is the displacement on the real beam at point C. Let's double check our answer. Again, from the same reference, we can see that delta max at center is 5WL to the fourth 384 EI. And that's the end of this tutorial. I'll hope to see you in future ones. Thank you.